desperately to get the quiz made up quickly.
That's fine. I'll be free. Some days I'm not, but today I am. Okay?
Thank you.
You're welcome. Can you shut the door behind you? Thanks. Alright, we're going to start our next unit today. I passed these out previously and I asked you to put them in your binder or notebook just to hold on to them. Does anybody need one? If you weren't here when I passed them out. No? Alright. In this unit, we're going to talk about logarithms. Maybe you've heard of these before, maybe you haven't. If you have used them before, it was either in Algebra 2 if you worked with them, or maybe in, I think, chemistry. Sometimes they use logarithms for solving particular problems. So we're going to investigate what these are and how they're related to the exponential functions that we were just working with in the next unit. Okay? So just to kind of get used to what a log is, because it is a different type of operation that you're not really used to. We're familiar with adding, subtracting, multiplying, dividing, using exponents or powers, but logs is kind of that new thing to us. So whenever you're looking at a log, just so we know how to say it, you would read it or say it log base b of a. So in this case, we would read this as log base 3 of 27. Okay, that's how we would verbally say it. So just to label kind of what the b means and what the a means, the b is representing a base, just like how we had a base for exponential functions. But the a is actually referred to as the argument. Not like it's always trying to pick a fight with you or something, okay, but it's just referred to as the argument. So what we're going to try to do is take a look at how these logarithms work, or how these numbers are related to each other. And I want you to think about kind of exponents or powers like we were working with in the last unit. So is there any way that you can somehow use these numbers, 3, 3, and 27, to generate a true mathematical statement? Like something equals something else. What do you think about? Yeah. There we go. All right. 3 cubed equals 27. I like it. Okay. So taking a look at how that statement was written, let's see if we can write another statement for the next log. How can you use 2, 4, and 16 to create or generate a true mathematical statement? Go ahead, Ashlyn.
4 squared is 16.
4, 4 times 4? Yeah, it actually works out that way. This one, it's funny that it works out that way as well, but this should actually be 2 to the 4th. It's weird that it works out the other way too. Alright, what about the next one? Yeah. 5 cubed is 125. Alright, so if you take a look at those first 3 that we did, how would you describe the process of kind of converting a log equation to an exponential equation? Can you kind of describe where the numbers go? Yeah.
The base number
Uh-huh.
is... Good morning.
Good morning. Anything for the office? I think we're good.
Okay.
Thank you.
Nick,
Good, Hannah.
the base number is set to the power of what the whole equation equals, and that all equals to a.
Okay, so whatever the base is of the log, that's what the base is of your exponential function. So starts out as a base, it kind of ends as a base here. Whatever the log equals is the power on that base. And notice how the argument of the log would be kind of the answer of that exponential function. Okay, it kind of works out for all the other ones. We have a base of 5, power of 3, and an answer or argument of 125. Okay, so let's go ahead and keep writing out some of these true mathematical statements. So keeping that in mind, hopefully the rest of these make sense. We would have 10 to the third is 1,000. For the next one, we would have 36 to the 1/2 power equals 6. Do we remember what the 1/2 power actually represents? Yeah? A square root. And hopefully that actually makes sense to us. The square root of 36 is 6. Alright, so the next one would be 27 to the 2/3 power would be 9. Alright, we could actually kind of calculate this one in your head. Since you have a denominator of 3, that's like taking a cubed root. So what number can you multiply it by itself 3 times to give you 27? Since it's a cube root, we're looking for 3 times. What times what times what gives you 27? Yeah, 3. Okay, so the cubed root of 27 is 3. But then if you square 3, okay, that numerator of 2, you'd get 9. So that's how you can probably figure that out in your head. Let's try the next one. We would have 9 to the 5/2 power equals 243. Maybe we can check that one out in our heads. The denominator of 2 is signifying a square root. So the square root of 9 is 3. And if you were to raise 3 to the 5th power, I bet you would get 243. Alright, the next one we have 10 to the negative 6th power, 0.00, let's see, 1, 2, 3, 5 zeros. 1. We're used to scientific notation, right? 10 to a power moves the decimal place. That's essentially what's going on here. Next one would be 5 to the 1/2 power is the same as the square root of 5. Hopefully that makes sense because we can rewrite a square root as a 1/2 power, so those should be equal. If we check out the next one, we would have 4 to the 4/3 power is the same as 4 cubed root of 4. See, the next one we'd have 3 to the 1/5 power is the same as 3 to the 1/5. Hopefully that's blatantly obviously true. The next one would be 4 to the negative 2nd would be 1 over 16. You can make a negative power positive by moving it to a denominator, and 4 squared would give you 16. Alright, and if we quickly fill in the last 3, 5 to the negative 1 or negative 3rd, 1 over 125, 5 to the 1st is 5, and 6 to the 1/3 power is the same as the cubed root of 6. Okay, so we have this nice way to kind of convert between exponential functions, okay, a number to a power, and logs. And we're going to explore that relationship or that conversion a little bit more in this unit. Okay, so based on the examples, let's go ahead and make a conjecture, kind of what Hannah mentioned before, about the value of whatever a logarithm is. So let's go ahead and say that log base b of a is the power to which the base is raised to equal the argument. Right? So essentially the value or answer from a log is a power that you're raising a specific number to get a different number. So we're going to try to look at some relationships here between what the base is and what the argument is, and just try to figure out maybe some type of pattern in terms for us to figure out or make a guess as to what this logarithm value would be. So we're kind of going to compare in the bottom box here, what if the base is equal to the argument, what if the base is less than the argument, what if the base is bigger than the argument. So let's go ahead and in these little boxes, let's just label or write down the relationship between the base and the argument for each problem. So for instance, the base in this first one is 3, the argument is 27. Clearly the base is less than the argument. 3 is less than 27. So I want you to go through all the other examples and just label that relationship, whatever it might be. In the second one we did, the base was also smaller than the argument. The one below that, the base was bigger than the argument. Alright, so go ahead and label those different relationships. Alright, so looking at all those different relationships you labeled, can we find one where you said the base was equal to the argument? If that was the case, what was true about the value of the log? Yeah.
The plot, it was raised to the first power.
Uh-huh.
So
So log base b of a would always equal 1. If your base and argument are the same, what's the power you have to raise the base to get the argument? That power would always have to be 1 in order for them to be exactly the same. So if the base and the argument are the same, your log or exponent value in this case would always be 1. Take a look at the next one. For all the ones that you labeled the base was less than the argument, what do you notice about the value or answer from the log? Let's see, we had 3, 3, 5 halves, 4 thirds, 4, 1/5. Actually, this one's bigger than A. We had 3, 1/2. What do all those numbers have in common? Yeah. Alright, so the value of the log is bigger than 1. Alright, and then take a look at the other ones. If your base was bigger than the argument, we have -3, -6. Let's see, here we have 2 thirds, 1/2, -2, 1/2. So we might have like different things going on here. Sometimes we get a negative value, sometimes we don't. Alright, so let's check this out. We can have two things happening. Either the answer is less than 0, meaning negative, or we have some type of value between 0 and 1, almost like that exponential property we looked at when we did those graphs. We have 2/3, 1/2. So the other case is log base b of a is between 0 and 1. Can you describe kind of the condition or the stipulation? Like, when do we get a negative value? When do we get a value between 0 and 1? Do you see it? Go, Rebecca.
Well, if the value is, well, if the log equals a fraction, then it's raised to a power that is like below 0, it's like negative, and it's between 0 and 1. If sorry, I lost my logic.
That's okay. All right, so let's take a look at this. We have, in this case, b was greater than 0, or b was bigger than a, and our value was negative. In this case, we had another case where b was greater than a, but the answer to the log was 1/5. Okay, some number between 0 and 1. So let's go ahead and take a look at kind of the difference in the argument here. Notice how in this case the argument is less than 1, but in this case the argument is more than 1. So depending on what type of number a is, that's going to dictate what type of answer you get for your log. So when your answer to the log is negative, your a value is less than 1. But if your log value is between 0 and 1, your a value will be bigger than 1. Okay? I'm not saying we have to recognize these properties or memorize them, but it is a way for us to essentially check our work. For instance, if we're familiar that the base is smaller than the argument, clearly our log should be bigger than 1. Okay, the power would have to be bigger than 1. So these are just some connections or relationships that are at least noteworthy. Okay, let's go ahead and take a look at some other types of logs. So we are used to what's called a base 10 system. Whenever you count or you learn counting when you're very, very young, you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But then don't the numbers kind of repeat themselves? You do 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. You're kind of counting or repeating in a cycle of 10. That's what's called a base 10 system. For you computer people or computer programmers, computers use a binary system, meaning they only count in twos. They only use zeros and ones, and then the pattern repeats itself. So we're used to a base 10 system, okay, our counting system, and whenever a log has a base of 10, it's what's called a common log. So, for instance, if you look at this case here, log base 10 of 100 is actually the same as just log of 100. Since base 10 is so common, we don't really write the little base number of 10 because it kind of gets redundant after a while. Why write a little 10 every time you're using a log when it could be just understood or common that that's the base? Okay, so whenever you see a log without a little number there, that just means that the little number is an understood 10, okay, a base 10. So for instance, this would be log base 10 of 5, even though the 10's not written there. Okay, this would be log base 10 of 100 and log base 10 of 115. Can we figure out any of these log values in our heads? What power do you have to raise 10 to get 5? That might be a little difficult. what power can you raise 10 to get 100? Yeah, Rebecca? 2. We can do that one in our heads. All right, and then the other one, what power do you have to raise 10 to get 115? That one might be a little tricky as well. But this is when a calculator is going to help us. Okay, so on your calculator, there's actually a log button that we're going to utilize. Can you find it? Do you see it? It should be on the left-hand side. Okay, it says LOG, and whenever you hit that button, it automatically pops up log. Notice how you are not able to type in a base, so that means this is an understood common log, a base of 10. And whenever you hit that log button, a parenthesis pops up as well, means you have to type something into that log, and that's what the argument is. Whatever's inside the log is what you're going to type in. So for this one, we'll go ahead and type in 5. So the power we would have to raise 10 to get 5 would be 0.69897. Okay, if you wanted to test it, you could do 10 to the power of 0.69897, and notice how you practically get 5. Okay, so whenever you're finding the value of a log, you're actually finding the value of a power or an exponent. So we'll do 0.69897. Okay, let's do the same thing for the other one. We'll just type in log of 115. So the power you'd have to raise 10 to get 115 is 2.061. Maybe we'll round it. Alright, so your calculator does common logs, always a base of 10. That's what this button is for. Okay, but just like in the other examples on the front page, we might not always have a base of 10, even though that's the common one. Okay, so we cannot type in log base 3 of 81 on our calculator exactly as it looks. We're going to have to change it a little bit in order for us to utilize the calculator. So that's what we're going to check out here. Before we utilize the calculator though, can we think about what the answer or the power should be? Like, is it going to be between two numbers? So what power, roughly, do you have to raise 3 to get 81? Either exactly or close. Yeah. All right, there we go. So 3 to the 4th would give you 81. All right, so maybe we'll circle the 4 because that would be the answer to the log. Okay. Now on your calculator, what we're going to do is change this one log, because it's a base of 3, not a base of 10 like we need it to be, and we're going to rewrite it in this form. We're going to do log of the argument, which is 81, over log of the base, which is 3. Notice how when you write it this way, these are common logs because we're not really writing a little base in there. So you should be able to type this in on your calculator. We'll do log of 81, close your parenthesis, divided by log of 3, close the parenthesis again, and notice how you get 4. Okay, that's the same power or answer that we figured out in our heads or on our own. But now you have a way to check it on your calculator. Okay, we're going to try some other examples. Let's try to do the next one in our heads. What power do you have to raise 2 to get 1 over 8? This one's a little tricky. Good, Rebecca? There we go. 2 to the negative 3rd would give you 1 over 8. 2 cubed would be 8, but you need to make it negative because the 8's in the denominator. So the answer to this log would be -3. Let's see if we can get the same thing on our calculator. So we're going to change this base of 2 into bases of 10. That way we can type it in. We would have log of the argument over log of the base. If you type that in, you should get -3. Is it working out on our calculator? Can you get that? Okay. Now these first two were kind of easier for us because notice how we were actually able to get a number, like an integer value for us or for this logarithm, but some of these other ones might be a little tricky. For instance, what power can you raise 2 to get 9? That might not be an integer or a whole number, but can we kind of guess what the answer should be between, if you're thinking about your powers, or what the answer should be close to? Good. Say it again. A little over 3, so something between 3 and 4, because notice how if you do 2 to the 3rd, you get 8, but if you do 2 to the 4th, you get 16. And clearly 9 is in between 8 and 16, but since it's a little closer to 8, the logarithm value should be a little closer to 3. Okay, so we'll say between 3 and 4. But realistically, we should be anticipating something closer to 3. So on our calculator, let's do log of 9 over log of 2, and hopefully we get something close to 3. Looks like 3.17. All right, so that's the power you'd have to raise 2 to get 9. Let's try another one. What power do you have to raise 3 to get 36? If it's not a whole number, it's probably in between two whole numbers. Yeah. Okay, so 3 cubed is 27. 3 to the 4th is 81. And notice how 36 is between 27 and 81. So that's what we should be anticipating on our calculator. So again, something between 3 and 4. We'll do log of 36 divided by a log of 3. Let's see, 36 is closer to 27 than it is 81, so your answer should be closer to 3 than 4. What did your calculator give you? Good, yeah.
3.26.
I like it. All right, let's try another one. What power do you have to raise 4 to get 21? And if it isn't a whole number, what's it between? Yeah.
Between 2 and 3.
All right, so 4 squared is 16. 4 cubed is 64. Notice how 21 is between 16 and 64. So the value of this log should be between 2 and 3. Since 21 is closer to 16, we should be getting something closer to 2 than 3. Let's make sure that happens on our calculator. So log of 21 over log of 4. You get it? Yeah.
2.20.
2.20. 0. Okay, if you rounded, maybe you want to do 0.196, depending on how many decimal places you want to do. That's completely okay. All right, let's try the last one. So what power can you raise 3 to get 105? If it's not a whole number, what's it between? Yeah?
Between 4 and 4.
Let's see. Okay, so 3 to the 4th is 81. 3 to the 5th, 243. 105 is between those. So the power of the log is between 4 and 5. So on our calculator, log of 105 over log of 3. 105 is closer to 81 than 243, so our answer should be closer to 4 than 5. Did you get it, Emily? Yeah?
4.24.
4.24, 4.236, however many decimal places you want to get. How are we doing? Pretty good? Okay, so whenever you're evaluating a log, you're actually finding a power. Okay, the power you have to raise the base to get the argument. Okay, so at the very bottom, what can we conclude about the value of the log and this log of the argument over log of the base? They are actually equal to each other. Okay, it was kind of more obvious from the first two that we did because we were able to figure those out in our heads. We were able to figure out 3 to the 4th was 81, and notice how we got 4 whenever we changed the base. Okay, this little piece here, log of argument over log of base, is referred to as the change of base formula. Okay, it's a way for us to change, literally change the base of a log to a common log, which is a base 10. That way we can use our calculator. Okay, so even though you're starting with like log base 4, log base 3, log base 2, you can always convert it or change it to a log base 10 to solve on your calculator. Okay, so change of base formula, log of argument over log of base. Do you think we can remember that for tomorrow when we go over some more examples? All right, we'll stop there for today, and we're going to continue with logarithms the rest of this unit.